So to give you an insight on software-defined wide area networks, here is Denis Kolegov with software-defined WAN, secure communications design and vulnerabilities. Welcome.
Thank you for the introduction and thank you for being here. In this talk, we will consider SD-WAN secure communication features and related vulnerabilities. I'm working at Tom State University and I am also principal security researcher at Bison security company in Moscow. And I'm also SD-WAN New Hope and AISEC team member. SD-WAN New Hope and AISEC research, community-driven research projects related to implementation security of different hard cybersecurity platforms. Some disclaimers. The main is that this is my personal talk and I don't speak for my employers. The agenda. What is the project about? What is SD-WAN? Some vulnerabilities. And we will also consider some secure design aspects related to modern crypto protocols, security frameworks, and so on. The SD-WAN New Hope project targets implementation security of SD-WAN products, and it was started in 2017. We have investigated the following products, developed some special security tools and frameworks for scanning, fingerprinting, and there are free technical papers, and all resources are free and can be found on our GitHub. This is our team, and this is the last paper on SD-WAN New Hope, summarizing the entire 2 years research. Okay, why SD-WAN? At the present time, as you probably know, SD software-defined are everywhere: SDDC, SD-LAN, SD-Core, SD-VPN, and so on and so on. And there are many interesting SD-WAN news that talks about integration SD-WAN and cloud platforms, different secure technologies, different new kind of routing and so on. So SD-WAN is very hard technology, and it was very interesting to break the technology for our team. Okay, we will begin with SD-WAN definition. Guys, who of you know what SD-WAN is? Maybe someone is the one developer or is the one operation manager? No? Okay, so let's define what is SD-WAN, and the trivial definition is that SD-WAN is a specific application of SDN conception and NFV technologies to wide area network connections. And let's get started with a trivial example. There is traditional network composing of routers, switches, firewalls, gateways, and so on. In general, a basic property of those traditional networks is a service per device. For example, if we want to use a VPN, we must solve the following issues: how to route our traffic to a VPN, how to support high availability, where the gateways will be located, and so on and so on. And unfortunately, we must solve these issues whenever we would like to add a new function like DPI or ADPS, WAF, and so on. And in SD-WAN world, control and data plane are physically separated, and it's called SDN. A VPN can be described as an abstract interface and some functional behavior. Something like VPN is a network function. And this function is virtualized in the sense that there is no separate device in the network performing the function. And this conception is called VNF, virtualized network function. And now to provide VPN, you need to enable a special DNF, and the VPN feature will be run on every infrastructure, on container, on virtual machine, on appliance, and so on and so on. And this conception is called network function virtualizations. SD-WAN is SDN used within external connections and environment specific for wide area networks. And different use, different requirements, especially from security point of view, are very important in these networks. And this is trivial. The Verizon SDN reference architecture of SD-WAN. This slide does show that security communications should be one of the main concerns of SD-WAN, because there are a huge number of interfaces, flows, protocols, and it is obvious that they must be cryptographically protected. The crypto keys must be stored securely, the components might be authenticated to each other, and so on and so on. And now let's consider the examples of found vulnerabilities related to different secure communication features in the very popular and known products. And we begin with zero-touch provisioning technology. The basic idea of zero-touch provisioning is to be able to connect a new device to a network without any manual configurations. Let's see how different vendors approach this technology. For example, Versa SD-WAN uses a hard-coded password to authenticate Versa devices, and it isn't possible to change these credentials at all because they are hard-coded on a client-side JavaScript code. Arista Zero Security Provisioning provides a bootstrap environment for entire Arista EOS-based products, and it seems that Arista ZTP hates HTTPS because the document says that you must not use HTTPS in that protocols. Another very popular vendor, VMware VeloCloud product, suggests some cases when a connected edge router will establish a connection with controller which failed authentication, and you can enable certificate errors like in browsers and Chrome and so on, and skip all security checks. Another approach one vendor used in bootstrapping process is as follows. A connected router establishes a secure channel with a controller using TLS. Then the router generates a public-private key pair and send CSR request to the controller other TLS channel. the controller issues the certificate, and then the router uses this certificate on the control plane protocols. And the issue here is that a router can use an arbitrary name in common name field. As a result, an attacker gaining access to the device can create a CSR request with a sensitive name like controller_sdwan_example.org or orchestrator_sdwan.org and so on, and get the corresponding critical certificate. And this is the fragment of code showing that the CA server did not validate common names and issue a certificate for any input common name. In another SDWAN product, during this secure design review, we found an interesting vulnerability. Developers used AES encryption algorithm in CBC mode to protect provision URL containing a secret, like token or password and so on. And in this stream, there is a vulnerability to the very famous padding oracle attack. And if an attacker has an encrypted ZTP link containing encrypted token and has access to ZTP service as an oracle, he will recover the clear text using padding oracle attack. Now let's look at some vendors and how they approach crypto protocols. And Silver Peak product is our favorite example. Silver Peak does not follow crypto best practices. No AAD primitives, alt libraries, self-invented protocols, and so on. And during a pen test, we decided to look for different automation scripts for Silver Peak on GitHub. And we found a very interesting script. And it was strange that command line interface didn't have username and password parameters. The script used the hard-coded credentials. So we tried several devices on the internet, and it worked out, of course. And we were able to successfully connect to REST API because REST API and Web UI use the same credentials, of course. And the interesting question is why monitor's user password wasn't changed. There are several ideas. Hard-coded credentials on the server side. Another one, users don't know how to change credentials. And the last one is users think that a read-only monitor user is safe account with default password. But there is one interesting point called tunnel config and state. And two things. First, that method allows to extract all information regarding IPsec tunnels. And second, interesting thing that some information, that information is not available via traditional Web UI, only via REST API. The most interesting fields are, of course, pre-shared key and IPsec nonce. IPsec nonce in and IPsec nonce out. We all know that nonce means number used only once. But as you can see on the slide, there are several nonces with the same values. And actually, We don't know if these values are used as nonce or as initialization vectors for yes, because Celery peaks don't specify their crypto protocols. And we were not able to perform reverse engineering because we did not have any devices. It is black box analysis only. And let's create a trivial POC using these two users, Burp Suite. And this is yesterday's results. There are about 1,000 Celery peak devices on the internet. 15 devices have admin user, and 168 devices have monitor user. Now let's talk a little bit about hard-coded credentials. It seems that hard-coded credentials is a common security features for many vendors and many products. Several days ago, SecConsult published an advisory regarding this issue, hard-coded keys in FortiGuard. And the idea is that the researcher found that sent messages are encrypted using XOR encryption with a static key. And during our research, we also found a hard-coded key in Fortinet SD-WAN product, and that key was used to encrypt configuration passwords in config files. The next vendor is Citrix. Citrix SD-WAN used the same pre-installed RSA key pair and the corresponding certificate on all devices, on cloud devices, appliances, and so on. As a result, an attacker in man-in-the-middle position could use this private key to perform man-in-the-middle attack against management traffic between controller and orchestrator. This is SD-WAN design. As you can see, all devices, edge routers, controllers, orchestrator are provisioned using appliance keys, and those appliance keys are the same for all devices. The protocol uses TLS RSA cipher suite, so perfect for secrecy is not enforced. As a result, if we know RSA private key, we can eavesdrop all management traffic in global networks and local area network and so on. And this is protocol protected by RSA keys, and there are many critical endpoints, as you can see: get SSL token, upload config, download config, and so on. The next vendor, Versa. It should be noted that Versa is a reference SD-WAN product for many SD-WAN startups, for many SD-WAN developers. The same feature here. This is a script on GitHub, and a developer is using Versa 1, 2, 3 password. And the question is why scripts contain this password, and the answer is because it is impossible to change password in all Versa components, as you remember from Versa ZTP case. The next Versa components is Versa Analytics Driver REST API. It also uses HTTP basic hard-coded credentials. The next unsecure feature is clear text communications. SD-WAN products have multiple protocols on different planes, control planes, application planes, and so on, and sometimes vendors forget to protect those protocols. For example, this is one of protocols implementing a service on 1, 2, 3, 4 TCP port. This clear text. This is Brain for Net SD-WAN product. Brain for Net is a Russian developers, and the approach in this company is called no crypto, because all network services are unprotected. For example, gRPC-based protocol or OpenFlow protocol. Absolutely all protocols on this platform use clear text communications. Okay, the next question is what about TLS vulnerabilities in SD-WAN? Several months ago, it was published a very interesting paper about statistic on TLS padding oracle attack. And we decided do the same research, but related to SD-WAN vendors on the internet, because probably this product are not in Alexa top million websites. The method is pretty simple. We use TLS attacker framework, and we used our SD-WAN knowledge database containing about 9,000 SD-WAN nodes. And this is the results. About 7,000 SD-WAN nodes were available on the internet at that moment. And this is number of attacks and the list of products vulnerable to these attacks. And now let's talk about secure communications from a defensive point of view. And when I say secure communications, I mean secure zero-touch provisioning, secure control plane, data plane protection, encrypted overlays, secure zero-touch provisioning, and so on. And the secure communications in SD-WAN have the following peculiarities. Is it possible to use or not HSM or TPM? Huge numbers of interfaces, services, protocols, different SD-WAN edge devices like CPE or appliances, and so on and so on. And in this talk, I would like to discuss two problems. SD-WAN bring up and key distribution. What is SD-WAN bring up? SD-WAN bring up or bootstrapping can be defined as follows. All entities authenticate each other. Edge routers must securely join the SD-WAN network. All entities have identities in cryptographic sense. And there is very interesting and it seems secure Cisco's protocols that defines this procedure. And to do this, we need authentication mechanism, and in this SD-WAN world, two mechanisms are used: token-based and certificate-based on TLS protocol. But it should be noted that token-based authentication is pretty simple, but can lead to different vulnerabilities. Because if a CPE or a router doesn't have a HSM or TPM or another hardware-backed secure storage, all cryptography credentials can be easily obtained or copied if an attacker gains access to the device. And in this case, developers have to use a token-based approach. And the idea is to use SPIFFE and SPIRE framework. Does anybody know about these frameworks? Okay. SPIFFE is very popular in cloud software engineering framework. It is an identity framework, and SPIRE is SPIFFE runtime environment. SPIRE is an implementation of SPIFFE standard in Golang. On the slides, you can then see different materials, SPIRE 101, different examples, and so on. There are many different scenarios how to use SPIRE with Kubernetes, with Envoy, Istio, and so on and so on. And this diagram illustrates the main steps in node attestation within SPIRE. Here we use AWS platform and AWS-backed attestation method. The idea is the agent AWS node attester plugin can query AWS for proof of the node's identity and then gives that information to the agent. The agent passes this proof to the server, and the server passes this data to its AWS node attester, and then the server can validate proof of identity, create a SPIFFE ID in JWT or X509 format, and send this credential to the agent. And now the agent is authenticated. And the second step is a workload attestation. A workload calls the workload API on the host and requests SVID credentials. The agent attests the workload using workload attesters, Linux-based or container-based, and then the agent requests an SVID for this workload. And as a result, the workload is attested and has its identity. And one of the problems from a security perspective in SD-WAN is a great number of components. And the idea is pretty simple. Apply SPIRE framework to secure SD-WAN. SPIRE provides the following attesters: joint token, SSH keys attesters, TPM-based attester, and attesters for different cloud-based platforms. So we can use different of them depending on SD-WAN architecture. And to create the POC using our Spire framework, we need the following keys. Machine identity is a long-term key, and agent identity and workload identity keys within Spire framework. And we will use EX509 POP attester. And it is suggested that mission keys credentials are provisioned on factory, and Spire server has the corresponding machine key CA certificate. And this is trivial Spire commands for server side and for agent side, and using this command we create an entry for a ZTP workload running on each router and describe its identity and selector, and then we run on the edge router these commands, attest the ZTP workload and fetch the SVID identity. And there are several pros and cons to use or don't use Spire to secure SD-WAN. On previous slide, I gave a link to secure SD-WAN design document, and it contains very interesting discussion with Ivan Gilman, who is core developer of Spire framework. And the last question is key management. And there are many problems in SD-WAN from a cryptography perspective. And the main problem is that SD-WAN vendors have to invent or reinvent cryptography protocols to govern cryptography keys. There are many different protocols that SD-WAN vendors use. Modern protocols like WireGuard, Noise, and Quick, post-quantum protocols, or self-invented APSec-based protocols like AKLS, APSec, other UDP, and Silver Peak product. And the main question is how to manage cryptographic keys if there is no good RFC documents and standards. And in SD-WAN, it isn't possible to use peer-to-peer key exchange like in traditional networks or in web applications, because in SD-WAN world, peer-to-controller model is used, because network shape is not persistent, and entropy generation on a small CPE nodes may be not a good idea, and so on. And some vendors like Cisco are trying to create standards, but basically all vendors use custom self-invented key management protocols. And this is drafts available on data tracker site related to SDN or SD-WAN key management. And one of them is SDN-based APSec management. which defines the following 4 cases. And the main issue is that we can replace IPsec protocol to WireGuard or TLS, and within this standard nothing changes. So there is no formal proofs or security considerations forbidding using other protocols. And SDN-based flow protection is a very popular approach among SD-WAN developers, and the basic idea is as follows. A controller generates necessary credentials like private keys, transport keys, certificates, and so on, and send them over a secure channel, TLS 1.3, for example, to edge devices. And very interesting question, is it secure or not? And there are some issues that can be easily identified. The main problem is that one peer controller dictates the key entirely, and an edge router doesn't contribute to the key. And this means that if a controller PRNG is compromised, subverted, or insecure, there is no chance to get a key with strong cryptographic properties. And we have already known such examples in Juniper or Fortinet products. The second one is that security of the protocol must be analyzed. And the main and another point that designing secure mechanism is not necessarily straightforward. And we can provide a trivial example showing how we can create a vulnerable protocol where an attacker will be able to impersonate a controller within this SDN-based flow approach. Let's suppose that a controller has a weak PRNG. Then 2 protocols are used between controller and edge routers, TLS 1.3 and a protocol with a noise protocol framework. The controller generates a random curve to 5519 private key for noise and send it over TLS channel. An attacker can predict the noise private key due to weak PRNG, and then an edge router receives the private key, generates the public key, and establishes a new channel using nice protocol. And of course, an attacker knows these public and private key pairs. The issue here is that if we choose noise protocol pattern or implementation of that protocol is vulnerable to TCI attack, then the attacker can impersonate the controller, but not edge router. And what is KCI? KCI is a key compromise impersonation attack. This is asymmetric weakness, which allows an attacker to compromise a controller if an attacker knew a private key of edge router. And for example, in a very popular WireGuard protocol implementation, there is this check. The handshake responder cannot assume the connection. Connection is authentic until they have received at least one valid data packet. Okay, the next question. If you use WireGuard, you know that each party needs to know a peer static key. And the interesting question is how a party gets that key. And this is a question from WireGuard mail list, and the suggestion was to use key export mechanism. What is key export? The basic idea is that if 2 parties have already established a TLS channel, then they can derive new keys using TLS parameters. The basic idea is to use PRF function computed on master secret. And the question is it secure or not? And there is RFC 5705, which formally defines this method. And this is a formula that must be used to produce key export values. So peers must use master secret that is the same on both parties. Client random, server random, and context value like my secure protocol or something like that. And there is a paper that formally proves that key export for TLS like protocols is secure. I mean, mathematically proves that this construction is secure. This is some peculiarities within this paper describing what is the model that was used to prove this result. So we have three mechanisms: formally proved key export within peer-to-peer model, some bad mechanisms that use different constants like certificates as a pre-shared keys and so on, and some methods like SDN-based IPsec management or custom protocols like in server peak products that is security level is not known. Okay, the main idea is from secure design point of view that if we are using secure by design approach, SSDLC methodology and so on, cryptographic best practices, then we have a chance to develop a secure SD-WAN products. Thank you.